Welcome back. In this lesson, we are going to be looking at the T procedures as far as our inference for distributions. They're going to look very similar to the Z procedures that we saw in Chapter 10, except the difference is that we don't know the population standard deviation. So how do we deal with that? We're also going to see two sample test procedures and confidence intervals. So first thing, we have inference for a mean of a population. Again, this is specifically when we don't know the population standard deviation, because honestly, most of the time, we won't know that. So our conditions still has to be from an SRS, and the population has to be normally distributed, or approximately normally distributed, with mean mu and standard deviation sigma, both of which we don't know. So what do we do when we don't know that? We use what we do know, which will be the standard deviation of the sample. And this gives us what's called the standard error. So now here we have the standard deviation of the sample divided by root n. Remember that what we've been using has been sigma over root n because we have a sample distribution, not just a sample itself. So we'll have s over root n. Our z statistic, if we remember back from last chapter, we had z was x bar minus mu divided by sigma over root n. Well, the t statistic, which is what we'll be using here, is basically the same thing, except we use s instead of sigma. And that gives us a t statistic, which will give us a t distribution, which is different than the z distribution. We'll end up using the t table. In fact, it doesn't give us a full-on distribution too. What it gives us is we'll have critical values. Because with the t statistic, we have another piece of information that we need. We need a degree of freedom. And the degree of freedom is just a sample size minus 1, n minus 1, for any of our one sample t procedures. That would be tests and confidence intervals. So what is the t distribution? How do we see it? It comes on the t table. For what we look at, that's table B, not the table B in our book that is the random digits. It's, I think, table C in our book or whatever, but it's specifically called t distribution table. A couple things that are going to be different here with the z table. First of all, this is all on one page. The z table, we had the negative ones, things less than the mean, on one page, and then the positive ones, things greater than the mean, on the other page. Another difference is with z, it was always the area less than, or the probability of getting less than that. Notice here, it's the probability of getting more than that value. If we look to the table itself, it differs from the z table. The z table had the first two digits in the left-hand column, and then the third digit in the top row. Well, here the left-hand column is this df. That's the degree of freedom. And then the top row, we have the tail probabilities. That's the p-value. The t statistic that we get will actually be in the table itself. Or it probably won't be in the table, but that's what those values are. They're t statistics. Then we'll see what we end up doing with that. We've used this already. We've used this bottom row for our confidence levels, because when the degree of freedom is infinite, that would be the population. So the larger your sample size, the closer the t-table actually gets to the z distribution, which should kind of make sense, because the larger your sample, the closer it gets to the population. So what do we get from this? If we find a t-value, let's say we find a t-value equals 3. I mean, it won't usually come out to be a nice number like that, but we'll just say it equals 3. And a degree of freedom equals 10 because we had 11 in our sample. Seems like an interesting sample size, but that's what it is. We would go to the row where the degree of freedom equals 10, and we look for 3. Well, 3 happens in between those two numbers, which means the p-value is going to be in between 0.01 and 0.005, which means it'll be less than 0.05. Basically anything to the right of that will be less than 0.05, so this would be significant at the alpha equals 0.05 level. It works out like the p-value means the exact same thing as it always has. For our hypothesis testing, the procedures are the same. That 4-step toolbox, we need to identify the population, we need to name the procedure, check the conditions, we need to do the test. Before that meant z equals p equals. In a t-test, it'll mean t equals p equals, and usually degree of freedom equals as well. It's a nice one to put in. And then we need to interpret in the context of our problem. So what we do is exactly the same. It's just what that third step looks like is a little bit different. So for our t-statistic, we saw this a second ago. If we want our confidence intervals, it's the same thing, except instead of z, we have t, and then we have s instead of sigma. Did you guys ever notice that the two equations are basically the same? If we took this s over root n and multiplied it over, we'd have t times s over root n equals x bar minus mu. We can add the mu, subtract. Mu should equal x bar minus t times s over root n. It's just we have plus or minus because we don't know which side it's on, because notice these t's are always positive. So these equations aren't completely separate from each other. They're actually basically the same thing. It's just what part are we looking for? Here we're finding the t. Down in the testing, we're finding the t. In the confidence interval, we're picking a t based off of our confidence level, which you could do the same. If we wanted a 95% confidence level, you would just look there, and then you'd go up to our degree of freedom was 10, so our t would be 2.228 instead of 1.96. But we end up with a t star because we're picking the t based off our confidence interval. So that's just an aside. Robustness, that's a fun word. A robustness is the resistance to conditions being violated. Now, the conditions that are being violated are not the simple random sample. That is huge because remember, there are no fancy formulas or special techniques to deal with bad data. Bad data equals bad statistics. So we still need good data, but good data might not be normal. If the population's not normal, the sample might not be normal. So that is something we just have to roll with. And so the robustness is how much does that actually affect it? T procedures aren't as affected as Z procedures as far as lack of normality. But again, violating the SRS requirement does affect the T procedures. And they're also strongly influenced by outliers, just like the Z procedures, because it uses the mean of the things, and the outliers will affect the mean pretty significantly. So using our T procedures, when can we use them? Except in small samples, the SRS is definitely more important than the normalness. In a small sample, they're both very important. So what does that mean? If n is less than 15, so if our sample size is less than 15, we want it to be pretty close to normal. The central limit theorem doesn't kick in yet at that point, so we don't really want to use it if it's not normal or if there's outliers. If n is greater than 15, then it can be used even if there are some pretty big, or unless there are big outliers, or it's really strongly skewed. So it's like, all right, it has a bit of a skew to it. It'll be fine. Now, for large samples, so n is greater than or equal to 40, even if it is super skewed, central limit theorem's kicked in and we should be good. So we can still use it because they're robust like that. The power of a t-test. The power of a t-test is exactly the same as the power of a z-test. You do it exactly the same, except instead of the z formulas, use the t formulas. Refer back to chapter 10 to see that, or look at the examples in your book. Matched pair t procedures. So this is one of the procedures that we use. We could use it with z, but honestly, it's mostly done with t. Matched pairs is when we have two sets of data where each data set, they were paired together and we recorded for both pairs. We then subtract. Examples for this would be like a pre-test and a post-test score. We look at each student and we wouldn't be looking at the scores of the two, we'd be looking at the improvement, the difference of the scores. So a matched pairs test uses one data set. That is very, very important. It uses one data set. In the next section, which we're going to get to in a minute, we're going to be looking at two sample procedures. That is not matched pairs. This is one of the most common mistakes that is made with matched pairs. So if we have a data set, say this one, which is experimental limb, control limb, it's in newts, they're healing. These rates here don't matter. We do not care about those. The only data that we actually look at are the difference in healing data. So it's one set of data. And now notice we have various newts. We have newt 13, newt 14, newt 15, newt 16, etc., all the way up to newt 26. We can't rearrange this data. Like this 24 and this 25 go with each other. Those are both newt 13. That's matched pairs. Or it could be the first pair of people that are very similar to each other, the second pair of people that are very similar to each other. Or it could be we picked the different flowers that are very similar to each other and we're monitoring some sort of progress on something. Where splitting it up, like say putting the experimental limb and the control limb both in numerical order, wouldn't make sense. And so we have these. We could do our T procedures on these. You could do them by hand. You could also do them in your calculator. You would enter these in, just in the difference column. And then we could do a confidence interval. So if we were going to do a one sample confidence interval, it would just be called a T interval in your calculator. We'd be using data in this case. I have my data entered so that we can see, and we'll find a confidence level of, let's go a 95% confidence level, and calculate. So you can check to see what you get, but my 95% confidence interval here is from negative 11.81 to 0.385. If we are going to interpret this, by the way, so we're looking for negative numbers because that means that the experimental limb is going to have a smaller value than the control limb, and being that healing rates a smaller value is good, the negative 11 is good, but what I notice is inside of this interval is 0. So no difference is inside of the interval. So as a test, this is not going to give us significant results. You would want both these values to be negative if you were going to use a confidence interval as a test. If we were going to do a test to get a p-value, so here would be 95% confident that the actual difference in healing between the experimental limbs and control limbs is in between negative 11.81 and 0.385 micrometers per hour. So let's do a t-test using that. And we want u0 0 because we'd want the difference to be less than 0. So for my test h0, we're going to have the mean of experimental minus control equals 0. That would be there's no difference. And generally speaking, with matched pairs, the mean will always equal 0 for your null hypothesis. And then the alternative, experimental minus control, is less than 0 because we're trying to show the experimental limb is a quicker, less healing time than the control limb. So we have that. We check our conditions. I'm going to assume that they're good. Phase 3, then we're going to do a one sample t-test for matched pairs. We want to give the equation or the test by either name or formula. By name is good. We can do our test. We get t equals negative 2.02. Degree of freedom was 2, 3, 4, 5, 6, 7. So we have 14. So degree of freedom would be 13. And the p-value was 0.032, which is significant because the confidence interval would have given us the two-sided if it wasn't equal. So this one, being that we were only looking for one-sided, if we did the two-sided, it would have been 0.064, which wouldn't have worked. But since it was close enough, the one-sided actually worked. So the p-value is 0.032, so since the p-value of 0.032 is less than the alpha of 0.05, there is evidence supporting the theory that the experimental limb, heals faster than the control limb. So, as you can see, the test, it's the same as the z, except that we have t equals. You can go to your the slide before, the t-table, to see that this t-value of negative 2.02 will be less than the t-value for the 0.05 p-value at the top, but it'll be in between there. So I think it goes from 0.05 to 0.025, so it should be right in between those two. So you can see that I can't go backwards on my slide to show you. but it is there. So, but notice the procedure is the same. Doing it on the calculator, we get the exact same stuff. Having to go to a table, the table is used a little bit differently than table A, but the information that we get is still going to be the same set of information. So, was section 1. Section 2, we're going to be comparing two means. So comparing two means can be important because sometimes we don't necessarily have matched pairs. For instance, when we did our paper starship flying, we could do matched pairs if we wanted to, where we were seeing the difference between each person's throw. But being that these are new starships and each person's throw it didn't really depend on like what ship you were throwing. It was all kind of random. We could use the two data set as well. That gets a little bit fishy in there because it was the same person throwing, but we could have had, say, half the class do one ship, half the class do the other ship, if we didn't have time for everyone to do both, and we'd use two sample data. So our conditions for two sample data and comparing two means, the data of the SRS, the data is R, the data are two SRSs of two distinct populations. The samples are independent from each other, and the same variable is measured for both samples. So first, the same variable is measured for both samples. That should be a fairly obvious one because we're trying to compare the same thing. The samples are, so two distinct populations means that the populations are completely separate populations. It could be separated geographically. It could be different types of plants, different types of soils. It could be separated age-wise or gender-wise. For instance, we could be looking at the heights of senior boys and freshman boys to see do the boys grow during high school. In this case, we'd expect the senior boys to be taller than the freshman boys, probably, but that's what we do. We'd have two distinct populations. It wouldn't just be taking the boys at standard high school and getting two samples from that one population. Then the two samples are independent of each other, so they can't be matched at all. One of the ways that people mess this up is when they are trying to get the differences between males and females, they go to like a house and they ask the male and the female at the house the same question. They use that data. You would have to get a random sampling of males and then also a random sampling of females. They might end up randomly at the same house, but more often than not, they will be completely different houses that you would have to ask. And so that's one of the things that people get caught up on. But also specifically, these are not matched pairs. Other condition, both populations are normally distributed. Distributions mu1 and mu2 for population 1, population 2, and standard deviation sigma 1, sigma 2. And those are generally speaking unknown, but we do have z procedures here as well. So sampling distribution of x bar 1 minus x bar 2, as opposed to just x bar, we take the sampling distribution of the difference between them. The mean is just the difference of the means. It's easy enough. Standard deviations, however, aren't quite so easy because they don't add, but variances do add. So we can find the variance. So we're going to square the standard deviations. Remember, the standard deviations look like sigma over root n. So when we square them, we'll get sigma squared over n. And then we can add them together for the variance. Now, I love this because right here we've got a Greek letter sigma with a superscript, that's the exponent, the squared, with a subscript. Inside the subscript, we have x's with a bar on top and a subscript in and of themselves. All those are missing are exponents, which will come in another chapter. Anyway, the variances, we just add them, so it's the variance over n plus the variance over n. Now for standard deviation, we just take the square root of all that. So that's the standard deviation of the distribution for two sample data. If we wanted the standard error, which for the t ones, we would simply replace the sigmas with the s's and get that. And sometimes standard error is written SE as opposed to using that. So we have that. Look at our test statistics. So the Z statistic is x bar 1 minus x bar 2 minus mu 1 minus mu 2. That should be in parentheses there. Then over our standard deviation. The T's, same thing. And the degree of freedom here, we have two options because the two sample test statistic, again, does not have a t distribution like the Z statistic does. Our first option, we can have the calculator compute it. It's really quite accurate. And I'll show you the equation to it in a few slides. Option 2, you just use the smaller one. It's a conservative estimate, but it works, especially if you're just doing it by hand. So if you have a sample size of 15 and a sample size of 20, 15 smaller, so 15 minus 1, degree of freedom is 14. Usually it's going to be close enough that if it's significant, it'll be significant, or if it's not significant, it won't be significant. Rarely are you going to get something that's so close that that would make a difference. But it is best with large n's that are close together. So you wouldn't want a sample size of 4 and a sample size of 100. That would be kind of silly. And so we have these. When we're doing our hypotheses, by the way, for a two sample test, our null hypothesis, there are two options for this. Either mu1 equals mu2, or the null hypothesis, mu1 minus mu2 equals 0. Those two things are equivalent. Like, it doesn't matter which one you use. But the null hypothesis is that the two means are the same, however you want to write that. Because of that, oh, this needs to be in parentheses too. But because of that, both of these are actually 0. So we don't even need to write them in our test statistic. Here we could have z just equals x1 bar minus x2 bar over the standard deviation of sigma squared, sigma 1 squared over n1 plus sigma 2 squared over n2. And same thing with the t procedures, the t statistic. We don't actually need that mean in there. And then the alternative hypothesis is going to be the same. Instead of equals for either of these, you're going to have either greater than, less than, or not equal to. For confidence intervals, it's the same idea. The z interval, we're going to have z star times that's our margin of error, and then it'll be the x bar, x1 bar minus x2 bar is our estimate. And again, we're either going to see 0 in the interval or we're not going to see 0 in the interval is kind of the idea. And then same thing with the t-interval, except we use t-star, and we have the s's instead of sigmas. And the degree of freedom is going to be the same as what it was for the test statistic. As you can see, as we get into the two samples test statistics and confidence intervals, the calculator comes in handy more and more. So a couple wrap-up pieces here. We have the robustness. Again, we saw robustness a little bit earlier with one sample. Two sample procedures are more robust than the one sample procedures. In general, the rules are the same, except instead of just the one sample, just add your two samples together. So we're looking at 15, greater than 15, greater than 40. If you have two samples of 10, you add them together, that's 20. So unless they're super skewed, you should be good to go. The degree of freedom for the two sample test statistic. This is the equation for it. This is why we use our calculator to figure this out, because that's disgusting. But that is how you would find your degree of freedom for your two sample test statistic or confidence interval. Again, the calculator computes it for you, or just use the smaller of the two degree of freedoms. But this one is actually very accurate. It's generally speaking a decimal, as you can probably figure out by the equation. Always round it down. And then, again, it's very accurate when both samples are at least 5. And a sample size of 5 is basically nothing. If you have less than a sample size of 5, then you really need bigger samples. And then pooled two sample t procedures. This is something that was used in the past if the variances were equal. Now, how often are the variances equal or close enough to it to actually use this? Not hugely. It simplified the formulas a little bit, but we don't use it much anymore because we have the technology, we have calculators. So a simplified formula to make things a little bit easier, but you lost some accuracy, isn't as important now as it used to be back in the day. So that was chapter 11. Again, recap, we have T procedures, which are like the Z procedures, uses a different table, has degree of freedom, but it's specifically when we don't know the standard deviation of the population. And then we had the two sample procedures in this one. Make sure you're reading your book on this. I'm going through some of the basics, but there's more details and stuff in your book. That's huge. And as everything else, keep working problems, keep asking questions, and as always, happy mathing. Until next time.